All right, well, I hope everybody's having a good day. We will finish the composition of functions lesson today. We'll move right into inverses, and with any luck, we'll be done with that by Friday. That may take a little bit of time next week, but we will definitely be able to start the next unit, trigonometry, next week. So what's going to be happening in the following days and next week? Tomorrow, remember, is the final day to retake any of those remaining two grades. I'm talking about the Rational Inequalities exit ticket and the second exam from last week. So if you want to come on in, if you need to pass, let me know. We will get that taken care of. On Friday is when I will go ahead and start applying the points for those who turned in their difference quotient assignment on time, and then I'll just go ahead and submit the grades. But on Friday during class, hopefully we should be finishing up inverses as I said, but I'm also going to budget some time to work on a exit ticket for the difference quotient. All right, so I'm going to give you probably 15 or 20 minutes. You guys will be able to work on it together with your notes, and then we'll turn it in before you guys leave. That'll be the first grade of the next 6 weeks. We're going to carry that over. On Monday, that's when your homework is going to be due. Okay, this is one of those lessons where I was able to copy out the assignment. That's going to be due on Monday, and look to have a quiz over this material on Tuesday. So we'll talk about it Monday if you have any questions. Tuesday we'll have our quiz. And I'm even thinking, I haven't put one together yet, but later in the week, next week, probably Thursday or Friday, having an inverse quiz. And I'll let you know when the homework is going to be due as soon as I get that out to you. All right, but that's all I have as far as this week and next. Any questions about anything that's happening? Okay, well, help me out. Every class was different. Did we finish this first problem? So we not only sketched it, but we got the composite function. Okay, because after class yesterday, I got to thinking about the domain of composite equations, and I started thinking about a lot of the mistakes that students make as they move forward. So I decided to kind of come back today and approach this in a different fashion, because it really doesn't apply to the first statement, and I'll show you why. But here are two steps you really want to follow if you're going to go ahead and find the domain of a composite function. Okay, so first find the domain of the input or the inside function. Okay, what's important there, any restrictions that the inside function has, those are going to carry over to the composite equation, even if it doesn't look like that would happen. And I've got an example in just a few moments to show you that. Now, the reason this really doesn't apply to the first example, the input here was function g. Well, x minus 1 squared, what's the domain of that function? It's all reals. He's infinitely wide. So there are no restrictions that we carried forward, and we just went ahead and analyzed the graph of the square root of, I believe it was x squared minus 2x is what we got for the composition. Okay. But 2, we'll just go ahead and take a look at the composition equation itself, and then what's really important, we cannot forget about the original restrictions for the inside function. So let's go ahead and take a look at another example. Okay. Find f composed with g, so we're talking about f of g of x, given f of x is the rational parent, and g of x is the square root of x squared minus 1. Okay, so we'll go ahead and get the composite equation, the composite function in just a moment, but let's start with step 1. I need to know what the domain of this input function g is. All right, so why don't we go ahead and do like we did yesterday? Basically, I would look to avoid values of x that would give me a square root of what?
Negative.
Well, why can't I take square root of a negative? What's wrong there?
Imaginary.
It goes imaginary, so we want to avoid those x's, right? So think about what we did yesterday. Okay, we went ahead and analyzed the radicand. So don't worry about the square root. I'm just looking at x squared minus 1. So this one's going to be a little easier to sketch. It's the quadratic parent, just what? Yeah, it's just shifted down 1. Okay, so let's say the negative 1 is right here. So we know this parabola opens up, so we're going to have something like this. Okay. In fact, can anybody tell me where he would cross the x-axis? 1 and negative 1. There we go. So that would be a positive 1. That would be a negative 1. Does anybody want me to elaborate on how I got that? Or is everybody okay? All right. Now think back to when we were comparing graphs to 0. where we had like f of x greater than 0, less than 0. Same thing's going to apply here. So what did I mean graphically if I'm comparing it to 0? Like where would I find parts of the graph that are greater than 0? Prasanta, can you help me out with that? That's exactly right. When we compared a function to 0, we were comparing it to the x-axis. So greater than 0 was above the x-axis, less than 0 was below the x-axis. Okay? So the only parts of this quadratic that are above would be this branch right here, this branch right here. Okay, so those are where it's considered positive. So this little part right here where it's below, that's where it's considered negative. Now, the reason this is important, remember the graph itself represents where you're going to have positive or negative y values. And that's what we're really interested in here. So would everybody agree if I went ahead and said that the domain of the square root of x squared minus 1, based on what we see, would be negative infinity to negative 1 union 1 to infinity? Now, you'll notice I didn't cap those yet. Would it be a parentheses or a bracket? Okay, so Will says bracket. Does everybody agree, or does anybody say parentheses? Okay. It would be a bracket. We would go ahead and include those. Okay. Now, the reason we would include those is because what is the square root of 0? It is 0. We are able to take the square root of 0. So that's why those are included. 1 squared minus 1 would give me 0. Okay. Now, the important thing here is any value of x between the negative 1 and 1, that's why I got to exclude them. They're going to result in a negative y value, which, as we said, is going to give you an imaginary number. So we can't have it as part of our domain. Okay. Now, what these two steps are telling me here is that now once I go ahead and find the composite function, I still have to have this original restriction apply to the new function. Okay. Now, it may change, it may stay the same. Let's see what happens. Okay. So how did we do this yesterday? If I want to find the composite function for f of g of x, plug it in, plug what in? There you go. See, I don't have a numerical value, so I'm going to take the entire equation and I'm going to plug it in the other one. So the input for function f is the radical x squared minus 1. So 1 over x will become 1 over the square root of x squared minus 1. Okay, so the original restrictions that we got from function g still have to apply to this guy. We can't have anything between negative 1 and 1. But does anybody notice anything else? Okay, Philip, what do you think? The placement of the radical is very different here. So how would that change the domain that I have? What would I have to do with the negative 1 and 1? Okay, does anybody know where I'm heading with this? Okay, Will, what do you think? There you go. So simply because the radical is now in the denominator, I'm still using the same restrictions, no values of x between negative 1 and 1, but I have to go ahead and make the extra change, negative 1 to negative 1 not included, union 1 not included to infinity. Okay. Because let's say we didn't change those to parentheses. Let's say we left them as a bracket. If I were to go ahead and plug in 1, okay, for example, so 1 over the square root of 1 squared minus 1, well, that's 1 over the square root of 0, right? Now, it's true, we can take the square root of 0, but where is he? He's in the denominator, and we cannot take that. So that's why we had to change it. Okay. So that would be the domain of the composite function. Okay. Is everybody okay with that? Okay. Now, just to kind of drive this idea home, I went ahead and put together a new example. Okay. So I'm not going to worry about the last one that's in your notes. Let's do this one. Okay. F of x is equal to the square root of x minus 8. G of x is equal to x squared. Find the domain of, oh, erase part of that. That's g of f of x. And I also wanted to go ahead and do something different because all these problems have been taking f of g of x, but there's nothing saying that you can't reverse that. You could very easily have g of f of x. Okay, so I thought I'd go ahead and throw a problem in there like that. All right, So let's say I want to know what the domain of the composite function is. Well, before we even get to the composite function, I need to find the domain of what? Okay, there you go. I need to find the domain of the input. So the input function this time is f of x. All right, so f of x, the domain. Can anybody tell me what that is? And it's a radical, so we kind of have to be thinking along the same lines. Basically, we don't want any values of x that would result in a negative. So where would I have to start? What's the first value of x that's acceptable? There you go. So anything 8 or larger. Now, if it helps, we can go ahead and sketch this. Remember, the radical parent starts at the origin and just curves to the right like this. Okay. So the minus 8 is just going to shift it 8 units to the right. Okay. Because remember, when you add or subtract to x directly, you take the opposite. Okay, so his domain, everything from 8 on. So what's important is when I find the composite function, I can't forget about this restriction. So basically, the original input function says that you can't have anything less than 8. Anything less than 8 is not in the domain. Okay, so let's go ahead and find the composition. G of f of x. Well, that would be g of the square root of x minus 8. Okay, that's the input for function g. So this is going to be x squared, the square root of x minus 8 squared. Is that okay with what I did? I plugged equation g into, or excuse me, function f into function g. But what's going to happen here? Yeah. In fact, the square and the square root, they're going to cancel because they're inverses. In fact, we're going to be talking about that a lot starting today. So I just ended up with x minus 8. Okay. And see, this is where it can be very dangerous. What kind of function did I end up with? It's just linear, right? So if I were to go ahead and sketch this guy, let's say, he crosses down here at negative 8, and not the best sketch, but he would look something like that, right? Positive slope, crosses down at negative 8. So looking at that graph, what's his domain? It's all reals, because he's infinitely wide, right? But if we were to say that, we would be wrong. Okay? Remember, this is my composite function. He was created by plugging function f into function g. So the original restrictions have to apply to him. So even though, yeah, he's a straight line, he's infinitely wide, his domain can only be from 8 to infinity. Okay? And I got to thinking about that yesterday, and I wanted to make sure you saw one like that. Okay? The original domain restrictions have to apply to the composite function. Okay. Questions? Cool. Well, with that, we are done with compositions. Now, I say done with compositions as of right now. We're definitely going to see them again, especially in, 3 weeks when we go ahead and take the first 9 weeks assessment. Okay. All the review material, the rationals, composite functions, inverses, all of that's going to be on there. Okay. And I'll talk about that more as we get closer. But let's switch gears. Let's talk about some inverses. Okay. And we are finally here. This is our last review topic before we can get to the brand new material. Okay. Our goal, trigonometry, but mainly the unit circle. Okay. So let's see here. A lot of this first page is just going to be fill in the blank. We got a lot of vocabulary to kind of bring up. So graphs of inverse functions are reflections of the line y equals x. So that linear parent, he is your line of symmetry. If you ever have a graph and you want to see what the inverse looks like, well, you just reflect it across this line. Okay. Now, given a function f of x, the notation for the inverse is to put -1 on the letter. So we say f inverse of x, or we could say the inverse of x. But f is by no means the only name we can call a function. So, I gave you some extras here. You can have the inverse of g or k inverse, however you want to say that. All right, and what I gave you up here was a cubic and a cube root function, just kind of illustrating the line of symmetry. Okay, so what are inverses? The domain of a function is equal to the range of the inverse. The range of a function is equal to the domain of its inverse. So basically, if a point x comma y exists on a function, then on the inverse, that point would be y comma x. That's the core idea behind inverses. The x values and the y values will simply switch. The x's become the y values become the x values. And I've given you a little example right here. Let's say we have function f, whatever he happens to be or looks like. He contains the point -1, 2. Well, on the inverse function, it would become 2, -1. You'll notice the values themselves are not changing. The -1 still remains negative, the 2 still remains positive. It's just that we're switching their positions. The x becomes the y and the y becomes the x. Now, algebraically, you're going to be looking at the opposite operations. Whatever one function does, the inverse will undo that. Okay, so for example, if a function is adding and multiplying, then what would you expect to see in the inverse? What's the opposite of adding? Subtracting. What's the opposite of multiplying? Dividing. So those are the operations that you should see in the inverse. Okay, algebraically, they will undo the other. Well, how do you know if we have inverses? Composition. Okay, you need to compose the two functions to see if you get x. Now, it's not a coincidence that we got x. What does x represent when we're talking about inverses? It was the very first thing we mentioned. Okay, it's the line of symmetry. If I want to see what the inverse of a graph looks like, I can reflect them across y equals x. So if I compose the functions and get x, that guarantees me that they are inverses of each other. Now here's the thing. It has to be x. Even something like a negative, even if I simplified it and got -x, they are not inverses. You have to get 1x and that's it. Also, it has to work both ways. You have to try the inverse as the input function and the inverse as the output function. Do you think it's possible for the composition to work one way but not the other? Absolutely. It actually happens more often than you think. So if you were to try the composition and it worked, you got x, don't immediately say, okay, well, the reverse has to be true. Always check it. Okay. Well, one thing we like about our inverses, we want them to be functions. Okay. Come down. There we go. So if a relation and its inverse are both functions, then both functions are what we say is 1-to-1. Okay. Basically, it's going to pass what we call the horizontal line test. Okay. The horizontal line test. Now, we're already familiar with a line test, but we call it the what? Vertical. The vertical line test. Well, what does it tell me? If it's a function or not. Now, it tells me that by showing me if or if not two values of x repeat. Okay, remember, if the line hit the graph vertically in two or more places at once, well, it was not a function. The same rule applies here. You're going to have a horizontal line, and you're going to sweep it up and down. If it hits your graph in two or more places at any time, it is not 1-to-1. The horizontal line test tells me if any y values repeat. Okay. Now, I'll let you think about why that might be important as we move on to this last definition here. If each value of the dependent variable corresponds to exactly one value of the independent variable, meaning it passes the horizontal line test, no y values repeat, then the function is said to be 1-to-1. Okay. Now, not everybody in the previous classes knew this. When I say independent, am I referring to x or y? X. X is always the independent variable. We say y depends on x, or y is a function of x. Okay. So let's take this information. Let's go ahead and start putting it to some good use. Okay. On the next page, for each of the graphs below, we want to draw the line y equals x, the line of symmetry for inverses. Well, you'll notice I've already done that on each of mine. Okay, we want to answer the question, which of the functions are one-to-one? Which of the equations for each of the functions write the equations for each of the functions from the graphs, and then find the equations of the inverses graphically, okay, or algebraically. If I could read today, that'd be great. Okay, so let's go ahead and talk about what it means to be one-to-one. Okay. All right, so we have this transformed radical parent right here. Okay, you'll notice I've got a horizontal line. So I'm going to take the horizontal line, and I'm just going to move it up and down. Okay, now here's my question. Am I ever hitting that graph in two places at once? I am? No. There's no place where anything repeats. So according to this, it passes the horizontal line test. So that means no values of y repeat. This guy is one-to-one. Okay. Now, are we thinking it got close right over here? Or what were we thinking? Who was it who said it does hit twice? Talking about what, sir? That we're good? Okay. So this guy is one-to-one. But let's try B. Okay, so we have this quadratic right here. So I've got a horizontal line. Whoop, let me go ahead and grab this horizontal line. So I'm moving the horizontal line up and down through this graph. What do you think? Is he one-to-one or no? Definitely not. He does not pass the horizontal line test. He's hitting it in two places at any given time. So he is not one-to-one. See if I can do this with a mouse. Not one-to-one. Okay. So now let's try this last one over here. So I've got a cube root. So I'm sweeping this horizontal line up and down. Am I ever hitting it in two places at once? No. So what would you say about C? He is one-to-one. That means I have no values of y that repeat. Okay. So I'm going to come back up here. Okay. I'm going to go ahead and list. We had two that were one-to-one, both A and C. Okay. Now, why is this important to me? Like, B was the only one of the three that was not one-to-one. Right now, that kind of looks like not H, so let me fix that. Not one-to-one. Okay. What's the core idea behind an inverse? What are we going to do with the x's and the y's? We're going to switch them, right? So see, this is a problem. If I have repeating y values and I take the inverse, those repeating y values will become repeating x's. So this is predicting whether or not the inverse will be a function or not. So I'm going to be able to find the inverse of this graph, but it will not be a function. Okay, but we'll get there. Let's go back to A. All right. So let's call this graph f of x. And even before I go ahead and list it, is everybody okay with the idea of one-to-one now? The horizontal line test? Anybody confused by that? Okay. Well, can anybody tell me what function is graphed here? We know it's a radical parent. Okay. So what kind of transformations have we seen? I'll tell you, all these, there's no dilations. They're just shifts. So what would give me the graph there? Okay. So the square root of x plus 3. Is that it? And then minus 2. The whole graph was shifted down 2 as well. Okay, so that function is the graph that I see there. Okay. Now, one of the things you're going to be asked to do quite often is find the inverse. Okay. Now, you can only use that inverse notation, the -1, if the result is a function. We really like our inverses to be functions. Okay. If they're not going to be, then we can restrict them, and that's the last thing I'm going to show you. But do you guys remember from Algebra 2? How do I algebraically find the inverse? Does anybody remember? There we go. Okay, so you take x and y and you switch their positions in the equation. That's the first step. Well, remember, f of x, or whatever you're given, that's just y. Y equals the square root x plus 3 minus 2. So I'm going to switch their positions. X equals the square root of y plus 3 minus 2. Okay, so I've switched their positions, but how does this help me find the inverse? There you go. Basically, I'm going to solve for what? Solve for y. Okay. So walk me through this. What would be the first step? Okay, let's go ahead and move the 2 over. So that would be x plus 2 equals the square root of y plus 3. And Andrew, you were just telling me how to get rid of the square root? Square both sides. Okay, so if I square the left, I'm going to square the right. Okay, so one undoes the other. The square and the square root will cancel. Now you can go ahead and expand that binomial. I don't think it's necessary. I would just keep it as is. So what would y equal? Quantity x plus 2 squared minus 3. Okay. And here's always your last step. You need to decide, am I going to leave the y where it is, or am I going to replace it with the function notation? Okay. Is the inverse that I got, is he a function? Yes. Now we know he was going to be a function before we even found him, because the original function was what? 1 to 1. So guaranteed he's a function. So I can take this y and I'm going to replace him with f inverse of x. You can only use the inverse notation if it's a function. Okay. If it is not a function, you have to leave the y there. Okay. All right. Now, there may be something that somebody's thinking about. I'm going to go ahead and elaborate just in case. But we ended up with a quadratic, right? Which makes sense because we ended up with a function that was a square root. So let's graph this guy. This is a quadratic parent that's been shifted down 3. And where else? To the left 2. Well, think about it. This point right here is a -3, -2. So think about our translations. We're going left 2 and down 3. Isn't that just that ordered pair reversed? Just like we've seen? Okay. But this guy opens up, so he's going to look something like this. Does anybody notice the problem? Yeah. Is that symmetrical? See, I started with half a parabola, but I finished with a full parabola. Okay. Now, here's the thing on this. Let's go back to the original function f. Can anybody tell me his domain? How wide is the original radical? Everything from -3 to infinity, right? -3 included. The range, okay. Well, how tall is he? Everything from -2 to infinity, okay. Now, we know that the inverse is a function, so I can definitely use this right here, okay. But remember, here's that repeating idea, the common theme. What are you doing with inverses? The x's and the y's are what? They're switching. So I'm going to take the original domain and range, and I'm going to switch them. So the domain of the original is now the range of the inverse. The range of the original is now the domain of the inverse. See, all I did was switch them. Now, does my graph seem to violate what I ended up with? He looks like he's going from -3 to infinity. It looks like his height is okay. But what's wrong with his domain? According to this, he can only exist from -2 to infinity, right? Which means that I have to cut half of his graph off. So algebraically, I ended up with a full parabola, but graphically, he has to be restricted, okay, by the original range that we had, because those y's became his x's. Does that make sense? Is there anybody confused by that? Okay. All right, let's try another one. B. Now, what do we already know about B? Yeah, we know that the inverse will not be a function. Guaranteed that's going to happen, because this original is not 1 to 1. Now, that doesn't mean we can't find the inverse function, or the inverse relation, I should say. All right, so let's call this guy something different. You know, we always use F and G. Choose another letter.
Y.
Z? Okay. Well, typically we don't like x and y because we don't want to say y of x or x of x, because x and y are considered our generic variables as part of the equation. So I like z. Let's try z. Z of x. Now, can anybody tell me what function would give me the graph that we see there? Yeah, it's just the quadratic parent pulled down 2. So x squared minus 2. Perfect. Okay. Well, now let's go ahead and find his inverse. How do I do that again? Switch the x and the y. Now remember, z of x, I'm not going to write it out again, but that function notation, those are your y values. So if y equals x squared minus 2, x equals y squared minus 2. It's only the variables that switch positions. Anything affecting those variables, like the square, you'll notice he stays where he is. And now what?
Everything is solved for Y.
Yeah, solve for y. So what would I do first? Okay, plus 2. So x plus 2 is equal to y squared. Now, how do I get rid of a square? Square root. So the square root of x plus 2 is equal to y. And I'm missing something. Plus and minus. We solved algebraically and we took an even root. So we got to put plus and minus in front of it. Now here's my question. Can I replace y with z inverse notation?
No.
I cannot. This, what we ended up with, he is an inverse, but he's an inverse relation. He is not a function. Okay? So it would not be correct for me to replace the y with z inverse of x. Okay. And now let's go ahead and sketch it. All right. The square root of x plus 2, well, what direction would that 2 shift in? Left 2. Okay. And see, look at this point right here, the original vertex. That was 0, comma, negative 2. Now look at the point here, we have negative 2, comma, 0. Again, it's just switching those. So it's probably going to open like that. See, that would be the positive square root of x plus 2, and this would be the negative square root of x plus 2. Okay. Not the best graph, but it gets the point across. Okay. In fact, let's take a look at the domain and range. Okay. For the original function z, okay, well, how wide is the original function? There's all reals. He's infinitely wide. So negative to positive infinity. Okay, what about the range? Okay, only from negative 2 to infinity. Now, knowing that, I already know the domain and range of the inverse. So I'm just going to go ahead and say inverse. I'm not going to go ahead and use that z inverse notation, but I know the domain would be the range of the original. So he has to exist from negative 2 to infinity, and his range would have to be all reals. And let's see, if I compare that to my graph, is that what I get? Yeah, he's infinitely tall, and he only exists to the right of negative 2. Right. Questions? You guys remembering this from Algebra 2? The good old days? Okay. All right, let's try one more. How are we doing on time? Oh, we got plenty of time. Okay. So this one, we already said he is 1-to-1. So guaranteed his inverse is a what? It is a function. Okay. Now, I used F. Noe told me Z. What letter would we like to use on this one? A. Okay, A is the first one I heard. So A of X. Now, take a moment, write the function whose graph you see. Let's see if we can recognize what parent that's from. I guess you could say we're going to try to see if it's apparent to you. Oh, we have fun. So I'm not looking for the function right now, but can anybody tell me what parent it's from? Connor?
The cube root.
This is the cube root. There we go. Okay, so in fact, this is the cube root shifted one left. So hopefully you came up with the cube root of x what? Plus 1. Remember, we take the opposite when we add or subtract to x. It went left, so it'd have to be plus 1. In fact, how many people got that right? Correctly identified it as a cube root. Very good, very good. Okay. Well, now let's go ahead and run through the process. I'll get it started for somebody. So we want to switch x and y as we've seen. So x is equal to the cube root of y plus 1. All right. And who wants to come up here and find the inverse for me? Okay. Galen, you want to do it? All right. Okay, so to get rid of the cube root, we got to cube it. So x cubed equals y plus 1. X cubed minus 1 is equal to y. Oh, it looks like you're just hitting the taskbar there. That's okay. So a inverse of x equals x cubed minus 1. That's exactly right. Okay. And was she correct to go ahead and replace the y with the notation? Yes. Remember, we already knew this was going to be a function. Okay. Very good. X cubed minus 1. Okay. So, again, I am not the best artist. I'm in fact going to take some points off of this. Like negative 1, 0 would be 0, negative 1. I know it would cross here. We're probably going to look at something like this and like that. Okay. I know it's horrible. I know x cubed looks like that. Mine doesn't go as smooth as that, but you know, you get the idea. All right. Okay, good, good, good. Now this one is probably one of those exceptions where we really don't have to think about the domain and the range. Because think about the original function. What is the domain? All reals. What's the range? All reals. So when you switch them, the domain and range of the inverse are still all reals. So there's no restrictions here. Okay. Good. Good, good, good. All right. Questions? All right. That is as far as first period got, so we will stop there. And we will continue this tomorrow. Hopefully finish up the majority of it. Kind of see how that plays out. Yes.